Greetings and welcome to another installment of Quant Slob. This is 6 in our basic application series, and this time around we're going to close out our mini-series on probability sampling distributions. If you have not already, I strongly suggest you check out the previous installments in this mini-series. Just look for the probability sampling distributions mini-series playlist. Most people will have at least heard of the central limit theorem, and probably so too the law of large numbers. These are two of the most celebrated theorems or results, at least traditionally, in all of stats and data science. And anytime a result is known universally by its abbreviation, it's probably usually pretty highly regarded. In stats and data science, if somebody says or writes CLT, everyone knows it means the central limit theorem, and same essentially for LLN. Some of you may have proved as an exercise the CLT and or the LLN in an upper division math or stats course. Some of you may know very little about these two essential theorems and wish you knew more, rightly so. If you've enjoyed the previous 4 editions in the sampling distributions mini-series, you do actually know about the central limit theorem and the law of large numbers. Part of our job here in this installment is to bring together what we've seen and learned. Reflecting on our 2 examples involving infinite populations, we drew theoretical samples of increasing sample sizes from an infinite imaginary population of every possible toss of a coin, and looked at the sampling distribution of the sample statistic proportion of heads in the sample. And we drew theoretical samples of increasing sample sizes from an imaginary infinite population of every possible spin and ball landing of a European roulette wheel, and looked at the sampling distribution of the sample statistic average net winnings for a player on a $1 straight wager on green 0. And I want to stress that in this sampling distributions mini-series, our emphasis is on observing patterns visually. So in the following graphs, I want us to pay close attention to a couple of things. I want us to notice how the green path, and you'll see what I'm talking about here, more and more closely hugs our sampling distribution as the sample size increases. The other is a little bit trickier, especially when the sampling distribution is lopsided, but it's true. The sampling distribution, that is the purple lines, balance like a seesaw on the true population parameter value, which is marked in our graphs by the tall, thin black line. Coin tosses, revisiting that. We looked at that in part 3 of this mini-series. Here's the sampling distribution of a theoretical sample of one element, and you can see I've added the green path here. Sample size of 10, and again, the green path sort of follows the tops of the purple lines. Sample size of 100. Notice that the green path here seems to follow the distribution, the tops of the purple lines, quite nicely. And sample size of 500, which is sort of where we just left off. The green path hugs our sampling distribution very nicely. And here, all of these sampling distributions are symmetric here with the coin toss. So it's not difficult for us to believe that the sampling distributions all balance on the thin black line here that marks the population proportion. We also considered the imaginary population of every possible spin and ball landing of a European roulette wheel. The probability sampling distribution of our sample statistic average net winnings for a theoretical random sample of size 1 is lopsided or skewed, as in skewed to the right. Here, the green path very poorly traces our sampling distribution. However, it turns out that the distribution, the 2 purple bars, do in fact balance at the black line. You can see that even though you got a little blip way out here, it's exerting a lot of leverage. Here we are at a sample size of 100, sort of bell-shaped but clearly lopsided or skewed. At a sample size of 1,000, we notice the sampling distribution is still a little bit skewed. We can see this green path pretty closely follows the tops of the purple lines, but we can visually detect some imperfections in the way it traces the distribution there. 10,000 seems to follow the distribution much more closely. 100,000 more closely still, and finally a theoretical sample size of 1 million The green path very tightly hugs the sampling distribution, I mean, from the best we can tell visually. And because of the symmetry here, it's not at all difficult to believe that the distribution balances at the population parameter, the black line. Defining the CLT can be pretty technical. The central limit theorem states what we've been observing throughout this mini-series. As our sample size grows, the sampling distribution becomes symmetric and bell-shaped. The green path we were looking at is from a normal or Gaussian distribution. And just as a technical note, I scaled its height because the normal distribution is defined over a continuous domain or continuous quantities, and we are overlaying it on a discrete distribution. But our present goal here is to make visual connections with what's happening. And we're going to be detailing, to be sure, continuous quantities and their distributions in immediately upcoming installments here. If you will, recall from our foundational series that a proportion is actually an average. It's an average of an indicator attribute. We touched on that way back in the foundational series. Recall also from our edition on probability that closed out our foundational series, one result of our theoretical samples is that the expectation of a resulting quantitative random variable is precisely equal to the population average of the attribute values. And expectation is just a formal or fancy way of saying an average of a random variable. And it turns out that this implies that the expectation of our sample statistic here, sample average, is precisely equal to the population parameter. This critical mathematical truth is what we were observing here when we noticed that the sampling distribution balanced, so to say, on the black line that marked the population average. So like so many Legos, we're going to assemble the law of large numbers. No matter what the sample size, the sampling distribution of the sample average will be centered at the true population average. We saw that as the sample size increased, the sampling distribution of the sample average became more and more narrow. This last ingredient here concerning the Gaussian shape of the sampling distribution of the sample average is actually sufficient but not necessary for the law of large numbers. It basically assures us that extreme values are not excessively likely, in so many words. Okay, here we go. As we get a larger sample, the sample statistic, sample average, will become a more precise estimator for the true population average. And by implication, the possibility that our sample average will miss the true average by some amount or worse becomes less and less probable as the sample size grows. And one last thing here, because it's pretty important, returning to roulette, let's focus on the scale or span of the x-axis of 4 of our sampling distributions from roulette. With a sample size of 1, the span here, or if you prefer, the range of the x-axis is about $60 here. With the sample size of 100 over here on the right, the span of the x-axis is about $6. With the sample size of 10,000 here, the span of the x-axis is about 60 cents, if you can see that. With the sample size of 1 million, the span of the x-axis is about 6 cents. So we're going to put all this into a table. With a sample size of 100, the span of the x-axis is 10 times more narrow than the span of the x-axis for a sample size of 1. With a sample size of 10,000, the span is 100 times more narrow. With a sample size of 1 million, the span is 1,000 times more narrow. And so we see the pattern. It's shown here in the right column on the far right. The narrowness of our sampling distribution is related to the square root of the sample size. And this is no accident, and it's just not particular to roulette. It's not a coincidence. That is going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.